my name is Jason Lidmere. I'm a PhD student here at Rice. I work under Dr. Tirthak Patel on quantum computing. And so today I will be showing Quorum, which is a technique that does unsupervised anomaly detection with quantum computers. If you don't know what unsupervised means, it means that when we are going through our data set, we don't necessarily know what an anomaly is and what it isn't. So that kind of mimics a lot of the real world applications for data analysis. If you don't know much about quantum computing, in the next minute, we'll try to learn all about it. So this is a typical quantum circuit. It is how we represent our quantum programs. On the left side, you'll see the atomic units of quantum computers, which are qubits. And what a qubit is basically an analog to a bit in a classical computer. So you have these little things that are either in a 0 or 1 state, or some probability of being in both. So you could have like a qubit that's in 30% 0, 70% 1. We have 3 of those in this circuit, and if we read it from left to right, we see the next thing is an amplitude encoding block, which is basically an abstraction that shows how we would typically take classical data and turn it into a quantum format. If we move along further to the right, you see these 2 big green and then turquoise blocks filled with little gates. So you'll see things like the Rx and Rz gates, and then these X gates with lines going on them. The bottom line is that what these do is the single qubit gates, the Rx and the Rz gates, will alter those probabilities for 1 qubit, and those gates that have X with the lines going across do something called entangle the qubits. And what this does is basically it shares information across the qubits in a way that actually creates a larger system. Similar to how if you concatenate bits in a typical bit string, with 2 bits, you'd be able to present 4 possible outputs. It actually is the same with quantum computers, except each of these outputs will have their own probabilities attached to them. It's very important to understand that basically this is actually the core mechanism for how we do our algorithm. What's happening is basically we're taking some classical data, feeding it through some gates, and we're getting some output at the end. Now, in terms of how our technique works, we begin on the top left with an input data set. And so this is classical data. It could be something like a combined cycle power plant environmental data set. And then from that, we will basically subdivide the data into things called buckets, which are just random subdivisions of the data into chunks. We also create many copies of the data set, and each of these copies will get basically a different set of subdivisions. After that, we will drop some of the features uniformly at random. And the reason is that with anomaly detection, we can't do something like PCA since we don't really know what's going to be anomalous versus what isn't. And then after that, we do something called, basically, we compress the data down. So in typical autoencoders, if you're familiar with autoencoders, what ends up happening is you kind of throttle the data down to a smaller information bottleneck and then decode it from that compressed variant. And the idea is that anomalies will tend to you'll have a harder time basically detecting anomalies or reconstructing anomalies. And it's kind of the same idea here. We basically compress the data down to a smaller set of qubits and then decompress it. And the idea is that we want to see what's anomalous based on that decompression. After doing that, we do this thing called a swap test. What you have to understand is basically that's just basically measuring how the data point that was originally put in changed from basically its variant that actually went all the way through these encoders and decoders. What we noticed when we were doing this process, so actually to summarize very briefly, the process is basically we take this data set, we run it through this process of these circuits, encode, decode, and get some result. What we notice is actually this is a machine learning technique where you train the encoder and decoder to do this really well. But with quantum computers, you actually don't need to train them at all. You just have to create a bunch of random circuits, feed them through the random circuits, and if you do it enough times, anomalies will stand out based on how much they vary compared to the other data points that have been run through the same circuit. So using this technique, we compared it on the left side to a quantum neural network, which is another quantum technique that can be used for anomaly detection. And you'll see that we have a few metrics. The main metric to look at, though, is the F1 score, the bottom left, which is the harmonic mean of the precision and recall you see above. And you can see higher being better, that Quorum does outperform the QNN. And on the right side, we took basically all the data sets that we tested, which were a breast cancer data set, the power plant data set, and then 2 lexicographic data sets, just like handwritten digits and stuff like that. And we sorted the data points after they were fed through these circuits based on those anomaly scores that we developed. And we noticed that within roughly the first 10% of the data on this sorted data set, we were able to detect almost all the anomalies, about 80% for the breast cancer and the power plant data sets. You also notice that we did some noisy runs because quantum computers are notoriously noisy. And we notice that noise also doesn't really have much of an impact, probably because we're doing a lot of aggregation across many random runs. And with that, I'll conclude my talk. Please come by my poster. Thank you very much.